Hello, my dear students. Today we are going to discuss about the unit 4 filters. It contains the characteristics of ideal filters, low pass and high pass filters, attenuation and phase shift constant, and M derived filters, band pass filters. Normally, the filter means it will filter the unnecessary frequencies, either lower band or higher band or sudden frequencies. Based on that, it may classify the low pass filter, high pass filter, and band pass filter and band elimination filter. So during the filtering process, some essential constants we are considered, that is the attenuation and phase shift. So these are all the major content we are going to discuss in the unit 4. Generally, the filter is an electric circuit that is designed to pass a specific band of frequencies, and it may used for the selective circuits, and it has been classified as active and passive filters, and it may used for the separation of signals according to their required frequencies, and it may widely used for the communication and signal processing applications. Mostly the filters are classified: the low pass filter, high pass filter, band pass filter, and band elimination or band reject filter. These four types we'll discuss one by one. The low pass filter means it will allow the frequencies up to the certain frequencies from the 0 to cutoff frequencies. This band is termed as pass band or transmission band. It means that this up to the cutoff frequencies, what are the frequencies required for the specific applications, it will be allowing from 0 to cutoff frequency. The remaining frequencies entirely stopped, that is the attenuation band or stop band. Similarly, the high pass filter means just opposite of the low pass filters. The lower cutoff frequencies from 0 to Fc, it may stop. The remaining higher frequencies, it may start allowing to for the specific applications. Similarly, the next type, the band pass filter. The band pass filter means it will allow the frequencies some specified regions. It means both the lower side as well as higher side has been stopped, and certain frequencies it may pass to the specific applications, the specific region of frequencies which is mentioned here, the F1 to F2. The band elimination or band reject filter means it is just opposite of the band pass filter, which is shown in the figure. Here, in previous case, the frequency has been passed from the region F1 to F2, but in this case, the frequencies has been eliminated from the F1 to F2. That is the major difference between the band pass and band elimination filter. So this was some ideal characteristics of the filters. They transmit pass band frequencies without any attenuations. The attenuation means is the stop band. It provides the infinite attenuation and hence they completely suppress suppresses all frequencies in the attenuation band. The next one, the transition region between the stop and bass band would be very small. Throughout the bass band, the characteristic impedance of the filter would match the circuit to which it's connected. Then only the circuit has been used for the specific applications. Then characteristics of the ideal filters we have seen. Then characteristics of the filters majorly consider these three constants, that is the propagation constant. The propagation constant P, it's denoted as P, should be real in the attenuation band and imaginary is the bass band. Then characteristics impedance, the characteristics impedance of the bass band should be the real, and in the attenuation band Z0 will be the imaginary. Then cutoff frequency, the frequency where the filter passes from the bass band to the attenuation band, and it's denoted as Fc, also termed as the normal frequency, because the practical filter does not have sharp cutoff frequency. Next, based on the filter characteristics, that is the propagation constant, phase shift constant, and the cutoff frequency, some are constant filters designed. See here, a constant filter is a T or pi network in which series or shunt impedance Z1 and Z2 are connected by the relationship. Let's say Z1 and Z2, it should be equaled R suffix k square, where Rk, the real constant, the Rk is the real constant and it's termed as the nominal impedance or design impedance of the constant K filter. So this is the basic relationship for the K filter. From that we can design our own filter, either low pass or high pass or band pass or band eliminations. So let us discuss the constant K filter for each case. The low pass constant K filter, the prototype low pass T or pi shown in figure. This is the T model. Then this is the pi network. So based on this, we are considering here for the low pass filters, we are considering the T network. So when we consider the Z1 and Z2 as the impedance, so Z1 is j omega L and Z2 is minus j omega C. Hence the Z1 and Z2, we seen the earlier relationship in the constant K filter, it should be equal to R K square. So first we are multiplying with the Z1 and Z2, j omega L into minus j omega C. So both the omega it may getting cancelled. Then the j into j square, the value is minus 1. Already the minus will be minus is there. So the minus into minus is getting plus. So the L by C will come. Since the product of Z1 and Z2 is the constant, that is the independent of frequency, we get Z1 and Z2, it should be equal to R suffix k square equal to LC. So if you are getting the Rk alone, if you are getting the Rk, it should be equal to the square root of L by C. We know that while we are finding the equivalent impedance of the T network, it's denoted as Z0 T. So Z0 T, it should be equal to Z1 square divided by 4 plus Z1 into Z2, which is already seen in the earlier expression, the last unit. So we are substituting the values of Z1 and Z2, will be getting simplified. So Z1 we know that is the j omega L. So Z1 square, we are making the square here also. Then Z1 into Z2, so we are multiplying here. So Z1 and Z2 we are already multiplied, that is the L by C. Then here while we are making the square, the J square omega square L square divided by 4. The J square value is minus 1. Here actually minus n is missing, but here we are considered. So we are commonly taking the square root of L by C outside. The remaining term will appear like this. So then Z naught of t, let's say Z naught t, that is the equivalent impedance. If the value of omega square C L divided by 4 value is less than 1 means that is the real value. If it is the greater than 1 means that is the imaginary. Since the cutoff frequency we can obtain from this expression, that is omega c square L c divided by 4 equal to 1. From that the FC, the cutoff frequency, it should be equal 1 divided by pi into square root of L into C. So from this the value of inductor and capacitor is like this. The L it should be equal to R divided by pi into FC, and C it should be equal to 1 divided by pi RK into FC. Here you have to notice it clearly while you are finding the inductance, the constant it should be the numerator, the capacitance, the constant would be denominator. Similarly, the phase shift and attenuation constant, normally phase shift constant it's denoted as beta, attenuation constant is denoted as alpha. So substituting that Z1 and Z2 values in the phase shift constant equations, these equations of T model also we are already derived in the last unit. So the cos beta it should be equal to 1 plus Z1 divided by 2 into Z2. So we are substituting these values and we are simplifying this 1 minus omega square CL divided by 2. But this is general equation. The Z1 and Z2 value it may vary according to the selection of networks. That is a common expression. The cos beta it should be call it as phase shift constant. We are substituting directly Z1 and Z2 values in the phase shift constant general equation, and finally we are obtained 1 minus omega square C L divided by 2. Since the alpha is 0, the band pass or phase shift beta is given by the omega c, it should be equal to 2 divided by square root of LC. Then the cos beta it should be equal to 1 minus 2 into omega square by omega c square. It means that here, that is the, while we are simplifying this expression, omega square CL divided by 2, it should be equal to 2 into omega square by omega c square, that we know that. So from that we are finding the phase shift constant beta, it should be equal to cos inverse of 1 minus 2 omega square by omega c square radians. So the attenuation of the low pass filter is given by the substituting the same values Z1 and Z2 in the general expression of the attenuation constant, that is cos h of the cos hyperbolic alpha, it should be equal to 1 plus, again here also the 1 plus Z1 by 2 Z2. So while we are simplifying this expression, finally we are obtained this, that is the 2 omega c square by 2 omega square by omega c square minus 1. So while we are taking the alpha alone, the cos hyperbolic inverse of 2 omega square divided by omega q square minus 1 appears. That is the attenuation and phase shift constant and constant K filter for the low pass filter. Similarly, we are moving the next topic for the high pass filter. Here also we are consider the prototype T section or pi section are shown here, but the Z1 and Z2 are different. There is the low pass filter means the Z1 it should be j omega L, but here Z1 it should be minus j omega C. So the entirely the Z1 and Z2 are entirely interchanged. That is why it may work opposite of the low pass filter. So the impedance value is entirely interchanged. So the signal also, the low pass filter means it will allowing the lower frequencies and banding the higher frequencies. Then high pass filter means it will allow the higher frequencies. So the impedance value is also it automatically interchanged. So the product of Z1 and Z2 remains the same, but here there will be because the Z1 and Z2 the product will be the same because of the values. Then the independent the same thing, that is the since the product is independent of frequency, the filter is constant K type. So Z1 and Z value it should be, we know that Z1 and Z2 it should be equal to RK square, then L by C we have obtained, then RK it should be equal to square root of L by C. We know that general expression, that is the equivalent impedance of the T network, the Z1 square divided by 4 into Z1 and Z2. So we are substituting the values of Z1 as well as Z1 and Z2. So we know that the Z1 is here is different, minus J divided by omega C, that we are substituted, then we are making the square and obtained the values and taken commonly the L by C and remains the same. Similarly, 1 divided by 4 omega square LC is less than 1 means it is the real part of the equivalent impedance. Suppose the value is greater than 1 means that is the imaginary part. Since the cutoff frequency FC is changes from the real to imaginary, so we are consider as 1 divided by 4 omega square LC equal to 1. So F suffix FC, that is the cutoff frequency, it should be equal to 1 divided by 4 pi square root of LC. From this we can obtain for the L and C value, that is the L it should be equal to RK divided by 4 by FC and C it should be equal to 1 divided by 4 by RK into FC. It was the constant K. Similarly, the attenuation and phase shift constants we are deriving with respect to the Z1 and Z2 values. So we are substituting the Z1 and Z2 values in the general expression cos beta, it should be equal to 1 minus the corresponding values. So 1 minus 2 omega square LC. Since the alpha equal to 0, then the phase shift constant, that is the beta given by omega c, it should be equal to 1 divided by 2 square root of LC. Then the cos beta it should be equal to 1 minus 2 omega c square by omega square. Then beta it should be equal to cos inverse of 1 minus 2 omega c square divided by omega square. Suppose if you are changing the relationship from cos and sin, trigonometry relationship, the beta it should be equal to sine inverse of omega c square divided by omega square radians. The attenuation of the high-pass filter can be obtained by the substituting of Z1 and Z2 values in the general expression. The cos beta it should be equal to, cos alpha it should be equal to minus 1 plus 1 divided by 2 omega square LC. So we are simplifying this, can get 2 omega c square divided by omega square. So finally the alpha it should be equal to the cos inverse of omega c square divided by omega square inverse. That is the case for the high pass filters. Similarly, the constant K type for the band pass filters. So the band pass filter also we are considered T and 5 sections if the series arms contains the series resonance circuits and shunt arms contains the parallel resonance circuits. When the resonance means that is the both inductive reactance and capacitive reactance is equal to 0. So that is the resonance, that's a series and shunt resonance. This is the, if it is the series arm contains the series resonance circuit, the shunt arms contains the parallel resonance circuits. That is the series resonance in all the cases. Then this is the parallel resonance. Similarly, the pi model, this is the series resonance, and these both two are parallel resonance. For these conditions equal to the resonant frequencies, that is omega naught, it should be equal to 1 divided by the square root of L1C1. It should be equal to 1 divided by the square root of L2C2. So it means that the both inductive product of inductive and capacitive reactance should be equal in the both the cases. Series and shunt impedance is given below. The Z1 it should be equal to j omega L1 minus j divided by omega C1. It should be equal to j. The same expressions we are taken commonly j in outside, and we are making the cross multiplication and simplifying this. Omega square L1 C1 minus 1 divided by omega C1, and the Z2 it should be equal to j omega L2 into 1 divided by j omega C2 divided by j omega L2 plus 1 divided by j omega C2, because here if the inductance and capacitance are connected in parallel, it will like this. So both are multiplying and here both are adding. So we are making simplification here, and the last denominator multiplied with the first numerator. So automatically these two terms are getting cancelled. The remaining this j omega L2 divided by 1 minus j omega square L2 C2 if the filter is the constant K type, because the Z1 and Z2 is the constant, then here also it should be the constant. So we know that L1 C1 it should be equal to L2 C2. So Z1 and Z2 we are already here multiplied. So the L2 divided by C1 it should be equal to L1 by C2, it should be equal to R suffix K square. So L1 C1 it should be equal to L2 C2. This is the general expressions which are derived here. Then the cutoff frequency is the Z1 divided by 4 Z2 it should be equal to -1. And the lower cutoff frequency is F1 it should be equal to minus Z1. Then upper cutoff frequency is F2 it should be value. It should be equal to it should be the values of Z1 will get the remains the same. So the multiplying the above equations by the j, we get the omega 1 L1 minus 1 divided by omega 1 C1 it should be equal to 1 divided by omega 2 C2 and omega 2 L1. Yes, while you are multiplying the j, the j value may getting cancelled, and here the j square will come, the j square value is -1. So we are making the simplification over here. Then 1 minus omega 1 square L1 C1 should be equal to omega 1 by omega 2 into omega 2 square L1 C1 minus 1. So it means that we are making the cross multiplication, and we are taking the commonly for the omega 1 as well as the omega 2. From this side we are taking the commonly omega 2, this side we are taking commonly omega 1, then finally we are taking the separation like this. So the L1 C1 it should be equal to 1 divided by omega naught square. So 1 minus omega 1 square divided by omega naught square it should be equal to omega 1 by omega 2 and omega 2 square divided by omega naught minus 1. Because L1 C1 we are replaced like this 1 divided by omega naught square. So here the value is getting changed, here also the value is changed. So finally we are obtaining this expression. So F0 it should be equal to the square root of F1 and F2, where F0 is the midband frequency, which is the series and shunt arms separately tuned. Then the lower cutoff frequency like this, Z1 it should be equal to -2 JRK. Then the values like this, 1 divided by j omega 1 C1 plus j omega 1 L1 it should be equal to this value, because this is the Z1 value. So we are substituted like this. From that we can obtain the expressions like we are making the cross multiplication, and we are shifting the denominator term into the numerator, that is by the cross multiplication. Then 1 minus omega 1 by omega naught square remains the same. The remaining the L1 and C1 values also we are replaced like this. Then 2 into Rk, omega 1 and C1. From that we can find it out easily. Omega 1 and omega naught, that is the 1 minus cutoff frequencies, like this F1 and F2, the ratio of F1 and F2 whole square, it should be equal to 4 pi Rk F1 and C1. Just we are replaced to omega in terms of frequencies F. So finally the C1 it should be equal to F1 minus F2 divided by 4 pi Rk F1 into F2, and we know that L1 C1 it should be equal to 1 divided by omega naught square. So the L1 it should be equal to Rk divided by pi F1 minus F2. The values of L1 and C1, we get the values of sun term. The L2 it should be equal to C1 Rk square, and it should be equal to F2 minus F1 Rk divided by 4 pi F1 into F2, and the C2 it should be equal to L1 by R suffix k square. So 1 divided by pi into F1 minus F2 Rk. So this all relationship can obtain the combination of this previous expression. So up to this, that is the constant K filter for the band pass filter, and the constant K type for the band stop filters. Here also the same, but it should be the just opposite of the band pass filter. The configuration of T and phi networks we are considered here also the same model, and the conditions of equal resonant frequencies, the omega naught L1 divided by 2 it should be equal to 1 divided by 2 omega naught C1 for the series arm, and omega naught square equal to 1 divided by L1 C1 for the shunt arm, and omega naught L2 it should be equal to 1 divided by omega naught into C2, and omega naught square it should be equal to 1 divided by L2 and C2. So based on this relationship, 1 divided by L1 C1 it should be equal to 1 divided by L2 C2 it should be equal to Rk. So based on this relationship, the L1 C1 it should be equal to L2 C2. Then Z1 and Z2 it should be equal to 1 divided by C2 it should be equal to L2 divided by C1 it should be equal to Rk square. And the output frequency, that is the F0 it should be equal to the square root of F1 into F2. And the cutoff frequencies, then Z1 it should be equal to minus 4 into Z2. Multiplying both the sides with the Z2 we get Z1 into Z2 it should be equal to minus 4 into Z2 square. It should be equal to Rk square. So the Z2 it should be equal to the plus or minus J into Rk divided by 2, because here the Rk also the square. So the Z2 it should be equal to plus or minus J Rk divided by the 2. If the load is terminated with the load resistance R, then R it should be equal to Rk, then the lower cutoff frequency Z2 it should be equal to J into 1 divided by omega 1 C2 minus omega 1 L2 it should be equal to J Rk by 2. Similar to that, the 1 divided by omega 1 C2 minus omega 1 L2 equal to R by 2, because both the sides are J, it may getting cancelled. So we are making the cross multiplication and making the simplification, and we are shifting the omega 1 C2 in the LHS side to RHS side. So 1 minus omega 1 square C2 L2 equal to omega 1 C2 Rk divided by 2. From the equations, the omega naught square it should be equal to 1 divided by L2 C2. So the 1 divided by L2 C2, just we are replacing the omega naught square. But here the L2 C2 is available, so we can replace in terms of L2 C2 into omega naught square. So 1 minus omega 1 square and divided by omega naught square should be equal to omega 1 C2 R2 by 2. So just we are replacing that omega term into the frequency term. That's the angular frequency and the frequency. So the 1 minus f1 square divided by omega naught, f0 square should be equal to rk phi f1 into C2. The omega 1 replaced in the frequency term. So the C2 then R phi. So the C2 it should be equal to, the C2 it should be equal to 1 divided by rk phi f1 1 minus f1 square by f0 square. Similarly the C2 also. The C2 again we are making the cross multiplication and obtaining the expression, and we are multiplying the frequencies which is the considered as commonly. So we are making the cross multiplication f0 minus f1, that is the f0 minus f1 is replaced like this, then f0 f2 minus f1 divided by f1 into f2, that is the sudden frequencies has been terminated or eliminated. So the L2 it should be equal to 1 divided by omega naught square, C2 should be equal to rk pi f1 and f2 divided by omega naught square f1 minus f2. Since the f0 it should be equal to the square root of f1 and f2, we know that. So we are substituting that expression. So the L2 it should be equal to pi into f1 f2 divided by 4 pi into f2 minus f1. So L1 by C2 and L2 by C1 it should be equal to rk square. Since the L1 it should be equal to rk square into C2, so rk by pi into f1 minus f2 minus f1 divided by f1 and f2, and C1 it should be equal to L2 by rk square. The C1 it should be equal to L2 by rk square. So we are substituting here 1 divided by 4 pi f2 minus f1 and the m derived filters. So the m derived filters alone we will be discussing the next class. So the up to this we are discussed the types of filters and the constant k and phase shift constant and the attenuation constant for the all 4 different types of filters. If you have any further clarifications, please send me the comment. Thank you for watching.